Okay, now we're going to talk about concavity. So we say a graph, a function is concave up. The formal definition is you're concave up on a region if all of your tangent lines live underneath the graph, below the graph in that region. And you're concave down if your tangent lines live above the graph on top of it. So if I had, say, some graph that looked like that, and I draw a tangent line right there. That tangent line's above the graph, above the graph, above the graph. This tangent line here. All of those tangent lines are on top of the graph. We would call this concave down. But if I had a graph that maybe looked like this, look at these tangent lines. Underneath the graph, I keep missing, but you know what I'm saying. Under the graph, under the graph. We call this concave up. Now, you don't have to memorize that. Like, I'm going to be honest with you. I didn't remember which way it went until I figured it out right before I said it. The way to think about concavity is a concave up graph looks like a bowl sitting on your table. You're about to make some cereal. And you got your bowl ready to pour the cereal into. Concave up is a right side up bowl. Concave down is an upside down bowl. You've just done the dishes and you're letting the bowl dry in the strainer. So you turn it upside down. That's concave down. The bowl was pointing down. So look at these pictures here. See, that looks like a right side up bowl. That looks like an upside down bowl. So concavity has nothing to do with increasing or decreasing. They've shown us 4 different pictures here to see that you can be concave down whether you're increasing or decreasing. It just means it looks like an upside down bowl. Look at both of those pictures. And concave up looks like a right side up bowl. It's the second derivative that determines concavity. Okay. And this one you might get backwards. I remember when I took this class, I would always get these backwards. So when the second derivative is positive, you're concave up. So this guy here would have a positive second derivative. When the second derivative is negative, you're concave down. You just got to memorize that. Second derivative positive is when you're concave up. Now, here's where that's going to confuse you, because look at that point right there. This is concave up. That means the second derivative would be positive. That spot right there is a local min. That spot right there. And here, I'm concave down. That means my second derivative on this entire region would be negative. That spot right there is a local max. We call this the second derivative test. That's the next slide here. And it's counterintuitive. Positive second derivative happens at mins. Negative second derivative happens at a max. I don't know. It always seemed to me like you would expect it to go the other way, that you would expect something positive to go with a max, but it's not. Negative second derivative happens at a local min. That's called the second derivative test. Of course, you never, ever, ever have to use the second derivative test. Second derivative test can sometimes fail. First derivative test is, I think, more reliable. Sometimes you do have, I shouldn't say you never have to use it. There are occasions where you have to use both, but I just find the first derivative test here to be more reliable. If the first derivative goes from negative to positive, you've got yourself a min. Okay, now what do we call points where the second derivative equals 0, where we switch from concave up to concave down? We call those points of inflection. Okay, so look at this graph here. There's a lot going on here. So let's break this down piece by piece. F, the original function, F is positive everywhere. Everywhere you look, it's always positive. Because I'm above the axis. Okay, what about the derivative? When the derivative is positive, your original function is increasing. So look, from here to here, the graph is going up. On that entire region, the derivative is positive. We're increasing. F is increasing. And out here, I'm decreasing. So the derivative is negative. See that right there and that right there. Okay, so that's just telling me whether the graph is going up or down. We haven't talked about concavity yet. Now let's look at concavity. Look at this part of the graph right here. That looks like a bowl of cereal, right? You just got a bowl sitting there. That's called concave up. Like it's a bowl waiting for you to pour some milk in it. And now look at this chunk of the graph. That looks like an upside down bowl. This is concave. Down. What you got to switch in between right there at that spot. It switches from concave up to concave down. That point right there is called an inflection point. And that's where the second derivative would be 0. So in this region right here, the second derivative was positive, concave up. And in this whole region, the second derivative was negative, concave down. Where you switch from one to the other is an inflection point. Where the derivative switches from positive to negative, you have local maxes and mins. Right there, the derivative changed from negative to positive. Here, the derivative changed from positive to negative. Where the second derivative switches from positive to negative, you get inflection points. You won't always have inflection points. The classic example of a place where you do have an inflection point is x cubed. Y equals x cubed. Like we could even look. The derivative is 2x squared. So the critical points, the critical values, where does that equal 0? At x equals 0. Where's my second derivative equal to 0? The second derivative would be 4x. Where does that equal 0? At 0. And then we could do an entire analysis. We could do a sign chart for the derivative. So here is y prime, a sign chart. That's my derivative. If I plug in a number less than 0, maybe, I don't know, -7. -7 squared times 2 is a positive number. What if I plug in +7? 2 times 7 squared. I'm just picking a random number, anything that's here. I get a positive. So my derivative says the graph is increasing, but then it pauses for just a second, has a horizontal tangent line, and then is increasing again. So this says the first derivative test says your function is always increasing. Okay, let's do a sign chart for the second derivative. Second derivative is just 4x. Let's plug in any value less than 0 to 4x. Negative 13 times 4 is a negative. Plug in any value over here. 12, 1. I don't care. Anything in this region. 4 times 1 is 4. That's a positive. Negative means concave down. Positive means concave up. So my function switched from concave down to concave up. That's why we have an inflection point at 0. And we could see that on the graph. Look right here. This is concave down. This chunk is concave up. It's always increasing. The graph is always increasing because it's always going uphill from left to right. That's why the derivative was always positive. And that point right there is an inflection point. It's also a critical value. Okay, let's take a look at this guy. And we're going to find all the inflection points. Now this, we got to be careful here. We're looking at the graph of the derivative. So let's write out some stuff here about the second derivative. So that's already the first derivative here. So we're taking the derivative of the derivative. So this graph here, let's separate it into all of its increasing and decreasing regions. So I'm taking the derivative of this. This is increasing, but I have a horizontal tangent line right there. The critical points of the derivative are at -1, at 0, at 1, and at 2. So look at the derivative of this. All those derivatives would be positive because the function's increasing here. So f double prime would be positive back in this region, hits 0, and then is positive again because all of the derivatives here would be positive. The derivative of the derivative, the second derivative, is 0 right there at 0, negative in this region, and then positive in this region. Oh, nothing happens at 2. I don't know why I put 2 on there. Nothing happens at 2. Positive. So where did the second derivative switch from positive to negative? Right there. That's an inflection point. Not on this graph, but back on the original. If we were to sketch out f, we would have an inflection point at 0. That's a good place to stop there.